Hi everyone! I thought I'd make a video on the rocket equation, just for fun. To derive the rocket equation, we start with something very basic: conservation of momentum. Think of the rocket's exhaust as being expelled in tiny chunks. If a small chunk of fuel of mass delta m is expelled downwards with velocity v sub e, the rocket is pushed upwards. Since the momentum of the entire system must be conserved, we can write the left-hand side is the total momentum before the small chunk of the fuel is expelled. M is the total mass, rocket plus fuel, and capital V is the initial velocity. On the right-hand side, we have the total momentum after the chunk was expelled. So the mass of the rocket plus fuel is now smaller by delta m, and the initial velocity has increased by delta v. The momentum of the chunk is delta m times the exhaust velocity seen by a stationary observer. That velocity is v minus v sub e. Since delta m is small, we can expand the right-hand side and keep only terms up to delta. Let's cancel some terms and rearrange others. Dividing by m and taking the limit as delta goes to 0, we obtain the so-called classical rocket equation. We can easily solve it, and then calculate what speed a rocket can achieve in empty space and zero gravity. m0 is the total initial mass, rocket plus fuel, and m sub f is the mass of the fuel, also called wet mass. This is a nice result because it only depends on the exhaust speed v sub e and how much fuel the rocket has. But it's also a boring result because it only works in 0g and no air resistance. So let's add those now. First, we write this equation in terms of time derivatives. Then we write the left-hand side of this equation as the time derivative of mv minus this term. Rearranging some terms, we can write a time derivative of the momentum on the left-hand side. But this is just Newton's second law. That means that this term must be a force of the exhaust pushing on the rocket. Now we can add the other forces we mentioned. Let's bring back these terms into their previous form, so we see the velocity explicitly. The mass derivative can in principle be any negative function. A positive function would imply we are somehow adding fuel mid-flight. But for simplicity, let's assume that it's constant. The fuel is being expelled at a steady state k. The coefficient alpha can be neglected as it is only dominant for small velocities. The coefficient beta is some function of the atmospheric density which depends exponentially on the height h. Similarly, the gravitational constant is not actually a constant, but depends on h as well. So we need to know how h changes with time. That's easy. h dot is just the velocity. So we get a coupled set of equations for v and h. So what can we do with this set of equations? Well, they are one-dimensional, meaning they describe a rocket that can only go straight up or down. But we can compute, for example, the maximum height a rocket can reach, given the amount of fuel and k, the exhaust velocity. Let's use some realistic numbers to see how a rocket that flies straight up can get. So, on the left here, we have the parameters of the rocket itself. I looked up these numbers for the Saturn V rocket, the one that carried astronauts to the moon. It's a massive rocket with m0, the total mass of 3 million kilograms, of which only 1.4% is the dry mass. The burn rate K on that rocket was about 14,000 kilograms per second, and the exhaust velocity was about 2,500 meters per second. The cross-sectional area of Saturn V was on average 70 square meters. On the right-hand side, we have numbers for the planet from which the rocket has taken off, in this case Earth. So, can this rocket escape the Earth's gravity? We know that the kinetic energy of the rocket, when the fuel is all burnt out, plus its potential energy must be 0 in order to escape. Solving for v, we get... Since r is much bigger than h, we can just write r. If we plug in the numbers for planet Earth, we get that the escape velocity is about 11.2 kilometers per second. Now we must solve these equations numerically up to t equals to k divided by m naught minus m dry. That's the time it takes to burn all the fuel. Plugging in all these parameters and integrating numerically, we get, drumroll, 8.67 kilometers per second. So even the biggest rocket in history cannot leave the Earth's gravity well without refueling in orbit. Okay, that's all for this video. If I decide to do a follow-up video on rockets, it will almost certainly be on the gravity turn. Until then, cheers.